Yeah, Radip, up to you.
Okay. Well, good evening, everyone, and welcome to today's session of this joint John Hopkins and IIT Delhi joint SMaRTs seminar series, where we host talks from academia as well as industry of experts and people who are working in the intersection of machine learning and applying scientific machine learning to physics-based problems. So, as you may know, that today we were supposed to host Professor Keith Warden, but his talk has been postponed due to some unforeseen circumstances. And in his place, we are delighted to host Mr. Dibyajyoti Nayak, who is going to be who is going to be presenting his work with Professor Somnatta Goswami, who is at John Hopkins. So, just to give you a brief background, so Dibyajyoti is a PhD scholar in the Department of Civil and Systems Engineering at John Hopkins University. And prior to that, he has earned his master's degree in computational and data sciences from IISc Bangalore, and where he was awarded the prestigious ANSYS MTech fellowship, right? And his bachelor's degree is in mechanical engineering from NIT Trichy, and his research lies in the intersection of applied mathematics, computational physics, and scientific machine learning, with a focus mostly on efficient and scalable AI models for advancing scientific and fundamental scientific problems. So today he will be speaking on the topic which is named as TI-DeepONet. I believe that stands for Time Integration DeepONet,
Yeah, that's
where
correct.
he would probably introduce a novel framework that will integrate neural operators with numerical time stepping schemes to improve the stability and accuracy in long-term predictions of the systems, right? So yeah, with that, Dibyajyoti, the floor is yours. Thank you so much for doing this. You can now start.
Okay. Yeah, thank you, Professor, for the kind introduction. Good morning, good afternoon, good evening, everyone. Uh, so, uh, so the topic of my talk would be TI-DeepONet, Learnable Time Integration for Stable Long-Term Extrapolation. So, uh, let us begin. Now, just to give some introduction, as you know, neural operators are basically help you map between infinite dimensional input and output function spaces, right? And everyone is very well aware of the different neural operators that exist today. So broadly, the neural operator frameworks inherently operate in two learning paradigms. So the first setting, as we call, is the full rollout, in which what we try to do is we try to represent or parameterize the output function space in terms of learned basis functions and coefficients. So for example, in the terms of like let's say if you consider the example of deep operator networks or DeepONet, the branch net basically learns the basis coefficients and the trunk net learns the basis functions. And then finally, we have an aggregation in which we can basically, parameterize the output function space in terms of those learned basis functions and coefficients. So the main idea here is that given an initial condition, we can basically predict the entire spatiotemporal output solution in just one shot. So that is what I mean by full rollout. The second kind of learning paradigm is known as autoregressive. So by autoregressive, what I mean is that given an initial condition, just like the way you do a numerical simulation, basically given an initial condition, you try to advance sequentially in time. You advance the solution state sequentially in time. We do the exact same thing, but in the sense by using neural network. So given an initial condition, we feed it into the neural network, you get the solution or the prediction at the next time step. And then this prediction sort of becomes an input again, which is fed back to the neural network in order to predict the time step, the solution at the time step after that. So this is what I mean by autoregressive or recursive predictions in time beginning from an initial state. Now, in these two learning paradigms, full rollout and autoregressive, there are majorly two problems that occur. So in the full rollout case, recall that I mentioned that we are trying to parameterize the output function space in terms of some learned basis functions and coefficients. Uh, if you're trying to represent the output space in this manner, then we are not inherently respecting the underlying causal structure of the system. So by the causal structure, what I mean is that let us say you consider a time-dependent PD system. Then intuitively, you know that there is an inherent dependency between the different solution states in time. Like the solution at time I is a function or is influenced by the solution at the time by the solution at all the previous time steps, basically from I minus one all towards back. So basically in the full rollout, we do not respect this causal structure. In the autoregressive case, as you can see, once you do recursive predictions in time, we are basically respecting this causal structure. But in practice, what we generally observe is that there is a huge error accumulation in time. And this is also intuitive, right? Because the error accumulation basically happens because at every time step prediction from UT to UT plus 1, you're basically, accumulating model approximation errors. And as you move forward in time, this model approximation errors sort of compound and they grow. So this is what I mean by error accumulation. So herein lies our motivation that we thought, okay, how can we try to, can we come up with some sort of hybrid approach in which first we are respecting the causal structure, which is inherent in a time-dependent system. And also, we are able to mitigate this error accumulation that typically happens when you're doing an autoregressive prediction. So in the subsequent slides, I'm going to show you how this error accumulation looks in practice by considering a simple 1D example. So before going into that, for our work, we take the candidate neural operator framework as the deep operator network. So this is a very popularly used neural operator framework in which basically there are two components. One, we have the branch network in which takes in input initial conditions, source functions, or it can be any material parameters, and then it sort of spits out a latent dimensional vector, which can be thought of as the basis coefficients. And then we also have a different second network, which is called the trunk network. So the trunk network takes in the input spatiotemporal query coordinates. By that, what I mean is the trunknet basically takes all those coordinates. Let's say if you're considering a 2D case, you have X, Y, and T. And then these coordinates are something where you want to evaluate the output function. So that's why we call it as query coordinates. And then the job of the trunk network is to basically take in this query coordinates and then spit out a latent dimensional vector, which can be thought of as the basis functions. And then finally, once you have the basis functions and the coefficients, you can do an aggregation and then basically represent the output function space as a basis function expansion, which you can see on this slide here. And then finally, you can minimize the loss and then you can sort of back propagate. So this is this is a very brief introduction about how DeepONet works. And now let us see how error accumulation typically happens in practice. So for that, we will consider a 1D viscous-Burgers equation. So this is one of the most widely used or one of the popular PDs, benchmark PDs that people use in order to evaluate the performance of neural operators. So the Burgers equation has this kind of form. As you can see, this has an advective term and this has the diffusion term. So this is nothing but the viscous dissipation term where you see the coefficient of viscosity sitting right in. And so for this case, typically what we do is we start. So in order to generate the data, we took the initial conditions as Gaussian random fields. You can think of Gaussian random fields as some sort of, a continuous input function or a continuous input field that you can use as an initial condition. And then we basically consider periodic boundary conditions since this equation is has second order derivative in space, we would need two boundary conditions. So both of them are basically periodic. And then these are some of the other details. We take 2,500 samples of initial conditions, and the spatiotemporal domain has basically a discretization of 101 time steps in time and 101 spatial grid points. Now, recall that in the autoregressive learning paradigm, we wanted the network to understand or maybe learn a mapping from the solution at a particular time t to the solution at a particular time t plus 1. So in order to basically mimic that, we have to arrange our data set in such a way so that we can enforce or we can make the DeepONet understand or learn this kind of mapping. Also, there was another question that we wanted to ask was that generally, let's say let's say in a more realistic scenario, you might not typically have access to the solution at all the time steps, right? Like but if you have, I mean, if you have a fast numerical solver, maybe you could generate data for all the time steps. But what if we want the neural operator to simulate further and further in time? So you cannot just keep on generating data for a longer time horizon, but rather we want to address the question that given the solution at a set of limited time steps, can we extrapolate or basically forecast beyond the scene training temporal horizon? So in order to basically mimic that setting, we consider in this Burgers case, we consider the first half of the temporal domain as a training time domain. So what that means is our training time domain is from t equal to 0 to t equal to 1. So what we'll consider is we'll just take the first half of the domain. So basically t equal to 0 to t equal to 0.5. And then we would basically treat that as our training data. So in order to enforce the DeepONet to learn the mapping from u at time t to u at time t plus 1, we basically consider the branch inputs to be basically arranged as stacked solution states starting from u at t equal to 0 to u at t equal to 0.5. And then the ground truth output, intuitively, you can understand that the ground truth output solution state should be shifted by one time step unit. So basically, uh, that's what you can see, right? So the time steps or the solution states for the ground truth output basically start from u at time step 1 and then goes on all the way to u at time step 50. So basically arranging the data set in this kind of way enforces the DeepONet to learn the mapping from time u at time I to u at time I plus 1. So another thing to keep in mind is that since we have arranged the solution states or basically our ground truth data in such a way, the time information is basically assimilated or absorbed into this data arrangement. So in that case, the trunk input, previously, if you're doing a full rollout, the trunk input would take x and t as the input coordinates. But in this case, since the time information is basically assimilated or absorbed in this data set arrangement, the trunk input would take only the spatial coordinates. So it just takes x as the input. Now let us see how the autoregressive error accumulation happens. So on this slide, I show you the predicted and the actual solution contours that was observed in the 1D Burgers example. And as you can clearly see that the predicted solution contours are way off and deviate significantly from the actual solution profiles. And on the right hand side, so on the left hand side, I show you the plots for two representative test samples. But on the right, we also we also try to have a more quantitative evaluation in which we try to see what is the relative L2 error growth in time. So you can clearly see that once you start advancing sequentially in time, the relative L2 error quickly grows. And then as you move further and further in time, the errors get accumulated, the error compounding happens. And then finally, once you reach the final time step, you can see that the relative L2 error has grown until 1.6. So that's like around 160% error in the actual solution, in the actual prediction. So clearly this is not acceptable. And we want to come up with some way in order to arrest or basically reduce this error growth. So For this, what we proposed, so in this work we basically proposed two architectures. So the first architecture, as we call it, is it's known as time integrator embedded DeepONet, short for TI-DeepONet. So the idea in this architecture is as follows. So in the pure autoregressive setting, what we were trying to do is we are trying to make the DeepONet learn the mapping from u at time t to u at time t plus 1. So instead, what we thought was that can we instead make the DeepONet learn the mapping from any input or from any solution state at time t to its corresponding time derivative at that particular time step. Now, there is a reason why we do that, which I'll come to in a bit later. But once we enforce the DeepONet to learn the time derivative at that particular solution state, we can use this computed time derivative and the corresponding solution state at that particular time, combine them in an ODE solver step. So the ODE solver is basically a one-step numerical time integration step. This module can basically use any kind of your favorite numerical time integration scheme that we have. It can be Runge-Kutta fourth order, Euler, or Adam-Bashforth, Adam-Morton predictor corrector methods. So basically, once we do that numerical time integration, we can sort of predict the solution at the time step t plus 1. And then we can compute an MSE loss between the predicted solution at time t plus 1 and the ground truth solution. So the reason or the main idea why we try to think in this way is that generally in a time-dependent PD system, you know that the evolving dynamics is basically characterized by multiple factors, right? And one of those things is basically the time derivative at that, or time derivative or the temporal derivative at that particular solution state. So in this way, the once we enforce the DeepONet to learn the time derivative for a particular solution state, this is basically more of a characteristic of the system, and this is not going to change once you exit the training domain and move into the extrapolation domain. It's still going to use that dynamics information and then use it and leverage that dynamics information in order to update the next state. So as you can clearly see that this is an autoregressive model, but framed in a different way where we have a hybrid approach. You have the neural operator part and you have the numerical time integration part. And secondly, this is a physics-aware approach because the numerical time integration part basically sort of enforces the physics which is governing the system underneath. Now, we went one step further and we basically proposed a second architecture, which is known as Learnable Time Integrated Embedded DeepONet. So this is just you can think of this as an elder brother of TI-DeepONet, sort of an enhanced version in which, like for example, in the normal TI-DeepONet, you did not have this branch. So I'm going to tell you the significance of this branch that we have in this architecture. So imagine in the vanilla TI-DeepONet architecture, you're using a Runge-Kutta fourth order to do this numerical time integration scheme, and which is also depicted in this picture, right? And just to give some context, in a fourth order Runge-Kutta method, if you want to do a time integration from a particular solution state at time t to t plus 1, we sort of compute. So this is a multi-stage numerical scheme, right? We compute the intermediate slopes between the two different t and t plus 1 time points, and then we take a weighted combination of this intermediate slopes weighted by certain coefficients. And that's why in a normal Runge-Kutta fourth order, you typically compute four intermediate slopes, which is K1, K2, K3, and K4. And then once you when you are doing the RK4 update, you basically weight those slopes by certain coefficients, which is nothing but if I'm not wrong, 1 by 6 K1, 2 by 6 K2, 2 by 6 K3, and then 1 by 6 K4. So what we thought was that can we instead make this, so this weighting coefficients that we have, right, 1 over 6, 2 over 6 and all, can we, instead of using a fixed set of coefficients, can we make them so as learnable? Now, there is a reason why we tried to think of is that way is that we wanted to see if you can use an adaptive numerical scheme, which is basically, which will adapt to the kind of input solution state which is coming into the branch network at this point. And this will also help us. So this adaptive numerical scheme would help us uh, capture sudden changes in the gradients or sudden changes in the dynamics depending on the input solution set. So this is exactly what we did. So this is what the second branch does. So this second branch that you see takes in the input solution state, passes it through a neural network. This can be a multi-layer perceptron, or there can be a CNN, any favorite neural network of your choice. And then it basically outputs a four-dimensional vector with the coefficients alpha 1, alpha 2, alpha 3, and alpha 4. And then these coefficients, the four alphas, can be thought of as the weighting coefficients analogous to the fixed coefficients 1 over 6, 2 over 6, 2 over 6, and 1 over 6 that we have in the standard RK4 scheme. So in such a case, the adaptive RK4 update equation becomes something like this, where instead of the fixed coefficients, you have the uh, learned slope coefficients, the four alphas that you can see. And then the rest of the process remains the same. You do a numerical time integration, you predict the next time step, and then you do a MSE loss, and then you do the back propagation in the normal fashion. So yeah, so in this slide, basically, I just wrote out explicitly what I mentioned, like what I highlighted in the previous slide. And so now these are the two architectures that we propose. So now let us, so in the subsequent slides, I'm going to move directly to the results. And we are interested in comparing the extrapolation performance of the different formworks. And by extrapolation performance, what I mean is extrapolating or forecasting the solution state beyond the scene training temporal domain, right? So that was one of the questions of interest that we wanted to address. And in order to do so, in order to have a rigorous evaluation, we take the examples of these 5 different PDs. Now, these 5 different PDs span a diversity of dynamics. Uh, they span complex high-dimensional cases. They have dissipative nature, dispersive nature. We consider a chaotic system as well. So we take into account different forms of PD dynamics, and we wanted to see how rigorous or how good our approach performs in these cases. And then for the predictions errors, as I mentioned before, we again consider a relative L2 error metric, which is given by this equation. Now let us directly move on to the 5 different PD cases. So the first case, let us circle back to a favorite example, which is the 1D Viscous-Burgers equation, where you have the PD, which is again defined in this way. The time and the space domain is basically from 0, 1. And here we have a decent value for the coefficient of viscosity. So you can imagine that this is, I see a question maybe.
Yeah, hi Dibyajyoti.
Yeah.
Actually, I have just
Yeah.
one
Hi.
question. Like in the OD solver, you are using Runge-Kutta method. So in this one, yeah. You are already estimating alpha 1, alpha 2, and alpha 3 by this another branch network. Then what actually happens in the OD solver? Because in the previous slide, we know that, okay, you used the Runge-Kutta method in the OD solver. But what happened actually here? So I got confused. So thought to ask you.
Okay. Yeah. Okay. I'll just clear that out again. So let's say you have a simple Runge-Kutta scheme, right? Now, let us basically think of this equation in the standard RK4 scheme. So ignore the alphas for now. If you don't have the alphas, then the Runge-Kutta update would look something like this, right? Ui plus 1 equal to ui plus delta t k1 by 6, 2 k2 by 6, 2 k3 by 6, and k4 by 6, right? That is the standard RK4 update that we all know.
Yeah.
So what we did was, instead of using those fixed coefficients, because no matter whatever the input function which is, or the input solution state which is going into the branch network, the RK4 update remains the same for all the solution states that have been seen as an input. So we do not want that. We wanted to add or maybe give some solution adaptivity to our architecture. So instead of using those fixed set of weight coefficients, the 1/6, 2/6, 2/6, and 1/6 that I mentioned, we use this learned set of coefficients alpha 1, alpha 2, alpha 3, and alpha 4. So you can think of this equation as a generalized RK4, in which for the vanilla RK4, alpha 1 becomes 1 by 6, alpha 2 becomes 2 by 6, alpha 3 becomes 2 by 6, and alpha 4 becomes 1 by 6.
Actually, my question is that I understand that you are using the trainable one. So once the trainable data that ui plus 1 you are getting, and also delta t by you are getting it from the DeepONet, what actually OD solver is doing here? So that is my con, because I thought like in the OD solver you are using Runge-Kutta method.
Yeah. So in this equation, you are interested in computing the slopes, right? K1, K2, K3, K4. So the first time derivative information that we get, that essentially becomes K1, right? That is the slope which we observe at time t equal to I, right?
Okay.
For the intermediate slopes, we again perturb this input solution state by an amount of delta t k1 by 2, and then we feed it back into the branch net, and then the output in that case would basically correspond to K2. And then in order to compute K3, we take UI plus we sort of perturb it by K2 by 2. We feed it into the branch net. The output of that essentially becomes your K3. So it is very analogous to the way we do the standard RK4.
Okay. So here you just
So actually, may I interrupt? May I interrupt? So I think so Dibyajyoti, we can actually rephrase the question that Rajat is asking. I think I'll also have the similar question. So we'll come to it probably towards the end of the seminar. You can continue now. We have the same question. I'll actually ask her the same question in a rephrased way. Is that fine?
Yeah,
Yes.
all right. Okay.
Okay.
Okay, sure. Okay, then I'll just move forward. Yes, so I think I was here. So yeah, so we were so the first example that we're considering was the 1D viscous-Burgers equation. It's the same example which I introduced in order to show you the error accumulation in time. The training details remain almost the same. As I explained before, we only take or we only give access of the first half of the temporal domain to the neural operator for training, and then we do the extrapolation on the other half of the temporal domain. So t equal to 0 to 0.5 becomes your training time domain, and t equal to 0.5 to 1 becomes the extrapolation time domain. So a couple of points regarding the characteristics of the PD. I always like to put out this so that we tend to gain or we tend to understand the physical nature of the PD that we are trying to consider. So as you can see, this is a nonlinear parabolic PD. The reason why I say nonlinear is because of this convective term UUX. And then you also have a dissipative term, which is basically given by this viscous dissipation term. So the Burgers equation is nothing but a simplified form of the Navier-Stokes equation, where you do not consider the effect of pressure terms. So let us look at the results. So we will mostly look at the results in this pattern. So initially, I will show you the results for a representative sample and how the solution profile changes in time. And then on the next slide, I will show you an overall quantitative assessment in which we see how the error accumulation in an autoregressive case is sort of mitigated. So we basically, for all the 5 PD systems that we consider, we compare 4 different frameworks. We have the DeepONet full rollout, which is nothing but our vanilla DeepONet architecture. We have the DeepONet autoregressive, which recall that I had what I had said about autoregressive is that it's a model which learns from solution at any time t to solution at time t+1 purely through the neural operator. And then apart from that, we also compare our 2 proposed frameworks, the TI-DeepONet and its learnable counterpart. So let us try to look closely uh, at the results. So first, let us focus on the autoregressive case. So in the autoregressive case, as can be expected, so the solid blue line is basically corresponding to the ground truth solution profile, and the red dash line gives you the predicted profile. So that is also mentioned here. And this is basically our training time domain, and this is our extrapolation domain. So in the autoregressive case, this is more or less expected, is that the the model starts accumulating errors early on at the initial few time steps, and this errors keeps on growing in time as you move further and further in time, right? And finally, once you reach the final time step, we can clearly see that the errors have grown to a very large value, and there is significant deviations from the actual profile. Now, in the full rollout case, as you can see, the predictions are much better. And especially if you see the training domain, uh, in the training domain, what the DeepONet full rollout is doing is basically interpolation. So this is a well-established fact that neural operators are very good at interpolation, right? And this is basically what is observed here as well. In the training domain, since full rollout had access to the solution in for this time steps, it was able to construct a set of basis functions, learned basis functions and coefficients, which are very accurately representing the solution states in this training domain. But once you exit the training domain and move into the extrapolation domain, recall that the basis functions and coefficients which are learned are sort of fixed, and they are learned only on the seen solution states in this training domain. So it is natural to uh, see that this basis functions and coefficients won't generalize well to the extrapolation domain because they haven't seen it. They're not, so the fixed basis functions and coefficients would not be able to learn the output solution in this particular extrapolation domain. And that's exactly what you see, that errors start cropping up and these errors keep growing in time, as you can see. However, on the other hand, the both of the TA-based frameworks do very well in the training domain, as well as once you exit the training domain, you can see a very good match between the profiles for the 2 cases, even in the extrapolation domain, which means that they have arrested the error accumulation and they have also given us good accurate extrapolation of the future solution states. And between the TA-based frameworks, the learnable one edges slightly ahead. And I'm not sure if this is visible, but it will be visible in the relative error plots that the TI-DeepONet turns out to be the best performing model in this case. And that is intuitive because we have given the TI-DeepONet a capability to adapt to the local solution at that particular time step. Next, as I said, we will move on to the relative error plots. On the left, as you can see, so we compare DeepONet autoregressive, DeepONet full rollout, and TI-DeepONet AB. By TI-DeepONet AB, what I mean is that, so this is one of the flexibility of the architecture, is that the OD solver can basically be anything. So during training, let's say we use RK4 during training to do the numerical time integration, but during inference, we can essentially use a different order scheme. So that's exactly what we did. During inference, we used an Adam Bashforth second order predictor method and an Adams-Moulton third order corrector method. So this is what I mean when I say TI-DeepONet AB. So this is the solid blue line that I had showed you in the previous slide. So this is the error accumulation that we saw in the autoregressive case. The red line basically shows the error accumulation in the full rollout case. You can imagine naturally that from t equal to 0 to 0.5, which was the training domain, recall that DeepONet full rollout was performing fairly well and was doing a good job in interpolation. That's why you see the errors almost matching closely with the TI framework. But once you exit the training domain, move to the extrapolation domain, you see an increase in the relative error. However, on the other hand, the green line which shows the TI framework, it has a very good and stable controlled error growth throughout the temporal domain. Basically, in the extrapolation domain, the error accumulation is not that prominent and it is sort of arrested. Next, on the right, we do a comparison within the different TI-based frameworks. So we consider TI-DeepONet AB, which is shown by this solid gray line. We consider TI-DeepONet RK4. So TI-DeepONet RK4 just means we use Runge-Kutta fourth order during training and inference. And this magenta line is basically the learnable variant, which is the TI-LDeepONet. And within the TI-based frameworks, as expected, the TI-LDeepONet basically outperforms all the other methods, which is also consistent with the solution profiles that we saw in the previous slide. We'll quickly move on to the next case. So this is the one-dimensional Kotevic-Debris equation, the KDV equation. So the 1D KDV PD has this form where the time domain is from t equal to 0 to 5, and the spatial domain is spanned from x equal to 0 to x equal to 10. So this PD is basically used to model wave propagation on shallow water surfaces, and the initial conditions that we take are basically sum of two solitons. So solitons are nothing but non-linear self-stabilizing local wave packets. So as they move in time, they do not change their structure. So you can imagine that this PD has some sort of dispersive nature. So in the Burger's case, we had a dissipative PD where you can see numerical dissipation in time. But here you can have a wave-like behavior, which is the numerical dispersion that we know. And these are more details about the data generation part. That's not important. But the key thing to note is that, again, we do a similar exercise. We cut short the temporal, like the training time domain. We give the first half of the training temporal domain from t equal to 0 to t equal to 2.5. And then we do an extrapolation on the other half of the temporal domain. Some remarks about the PD. Now, this is also a nonlinear PD where you have this nonlinear hyperbolic term. So this basically, this minus eta u ux basically gives rise to some sort of steep dynamics. And this third order spatial derivative that you see, which is sort of sitting here, this basically contributes to the dispersive nature of the PD, the wave-like propagation of the PD that I told you about. Now let us look at the results. Again, we do a similar comparison between the 4 different frameworks. We do it for one of the test sample. And in this case, what we observed was in both the DeepONet full rollout and DeepONet autoregressive cases, the underlying nonlinear dispersive periodic dynamics, which the KDV equation has, this was not captured well by the full rollout, by both the full rollout and the autoregressive as well. And it's natural to see that the DeepONet autoregressive error sort of explodes and grows to a very large value. But interestingly, in the full rollout case, the full rollout, so one of the key characteristics of this PD is that there is, due to the numerical dispersion, there is always a phase shift between the solution states and time. So this phase shift was basically not captured well by the full rollout method, and that's what you can see. Like the magnitudes are more or less in a comparable range between the predicted and the ground truth solution, but there is always a phase lag between the two learned solution states. However, again, on the other hand, between both the TI-based frameworks perform really well in the training time domain, and this basically translates well to the extrapolation domain. So this basically means that since we are having the numerical time integration, the TI-based frameworks are able to learn the underlying nonlinear dispersive dynamics, and this basically translates well to the extrapolation domain. And naturally, again, we see that between the TI and TIL, the TIL performs slightly better, which you can see here. And that is again due to a similar reason, which I mentioned before, because of the local solution adaptivity. We will move on to the relative error plots. Here again, on the left, we compare DeepONet autoregressive, DeepONet full rollout, and the TI-DeepONet. Again, you can see the TI-DeepONet autoregressive has a rapid and monotonically increasing error, and the full rollout has basically a non-monotonic error trend. So there's a reason for this non-monotonic error trend in the full rollout. So as you can recall, in the full rollout case, we are learning a set of basis functions and coefficients, and then we are trying to basically represent the entire output function space or the solution space in terms of those fixed basis functions and coefficients. So there is no there is no inherent meaning of doing a causal, like doing an inference based on preserving the causal structure. That's why uh, it's always an uncertain or a non-monotonic trend that you can observe. Like the basis functions might be able to represent the solution better in the extrapolation domain, relatively better, but not as good. But in the training domain, it might have a larger error. So that's why you say this non-monotonic error growth. Uh, Again, as expected in the TI-DeepONet framework, we see the error accumulation is sort of arrested to a large extent. There's a significant reduction of error in the final time step. And then on the right-hand side, we again compare within the three different TI-based frameworks. And again, as can be expected, TI-DeepONet, which is the learnable variant, emerges as the best method out of all. We'll move on to the next example, which is the one-dimensional Kuramoto-Shevchenskiy equation. So, so people from fluids and combustion might recognize this PD. So this is the PD which is used to basically model instabilities in a laminar flame front, and due to the kind of energy spectra, basically the energy transfer between the large scales and the small scales in the fluid flow, this is somewhat considered as a prototypical model for modeling fluid turbulence. And this is basically the training and the time and the spatial domain that is defined here. As one key thing to note is that I keep the training time domain to be infinity. That is because since this is a chaotic system, you can keep on simulating it forever, and it's still so. Uh, the main highlight of the case equation is that this has multiple, competing terms. You have this hyperbolic convection term, you have this anti-diffusion term. So by anti-diffusion, what I mean is you can think of that as a term having negative viscosity. So the viscosity basically contributes to stability in the numerical solution, but this is gonna do the exact opposite and destabilize the solution. And then you have a stabilizing hyperdiffusion term, which is given by this fourth order spatial derivative. And uh, eventually, the nature of this PD is such that it leads to the solution states being self-organizing into a chaotic state. So initially, you might start off with basically a non-chaotic or a mild dynamic state, but eventually, as you simulate further and further in time, the system basically translates into a chaotic state. So overall, this is a very complicated and a very challenging PD to handle. It has all sorts of notorious behaviors that you can expect. And in this case, again, what we did was we did not, do it. Of course, we do not do the extrapolation forever, but we took a finite temporal domain in which from t equal to 0 to 15, we had training time domain, and we took the rest half t equal to 15 to equal to 30 as the extrapolation temporal domain. Quickly moving on to the results. Again, we'll compare qualitatively the solution profiles, as you can see. Here, again, we do the comparison between the 4 different DeepONet frameworks. In the autoregressive case, you can see as expected, it accumulates errors early and it quickly deviates from the actual profile. In the full rollout case, recall that I had said, right, the full rollout is able to construct a set of good basis functions and coefficients and does very well at interpolation. Then it was able to capture the solution in the training domain. But you can clearly see a demarcation. Once you exit the training domain, move into the extrapolation domain, full rollout fails very quickly. And you can see the errors sort of beginning to creep up here. And there is significant deviations from the actual profile. Again, in the TI-based frameworks, they do a very good job. They are able to capture this nonlinear, mildly chaotic behavior in the extrapolation domain. And I'm not sure if this is visible, but within the TI-based frameworks, again, for an extended period of time, the TI-DeepONet basically outperforms all the methods and has a very good, stable and accurate extrapolation to the solution states. And which means that the frameworks have some sort of able to capture this rapidly changing stiff dynamics, which is there in the PD. Uh, Moving on to the relative error plots. So here you can see autoregressive. There is rapid error accumulation early on. It grows very quickly, and then we saw that it sort of saturates after a point once it reaches a certain threshold, and then the errors still keep on growing. In the full rollout case, you can clearly see that until t equal to 15, which is the training temporal domain, the relative L2 errors were quite good, as you can see, because you can see at some parts of the temporal domain, the full loadout has slightly better performance than the TI-DeepONet, but once you exit the extrapolation domain, you can see that the TI-DeepONet sort of has a more stable and controlled error growth. So one thing to note is that this is a chaotic system, and we do agree that the relative L2 errors were still high at the final time step, but the reduction was significantly more as compared to the other 2 frameworks. And again, within the TI-based frameworks, as expected, the TI-DeepONet edges ahead and does a better job than the other TI-based frameworks. We move on to the 4th example, which is the 2D Viscous-Burgers equation. So the 2D Viscous-Burgers is basically an extension of the 1D Burgers equation, but in 2 dimensions. And these are certain, training details, details about the initial and the boundary conditions. So that's not important for now, but we have basically a unit square domain where we have X and Y going from 0 to 1. And then the training domain is basically from t equal to 0 to t equal to 1. So in this case, until now, we were only doing 2x extrapolation. Basically, the first half is the training temporal domain, and the second half is the extrapolation domain. Here, we increase the difficulty 1 notch further. We shrink the training temporal domain to be 1/3 now of the entire temporal domain. So as you can see, t equal to 0 to 0.33, which is roughly 1/3, is basically your training domain, and the rest of the domain becomes your extrapolation. So let us move on to the results. So again, we compare the 4 different frameworks. So I'd give some explanation as to how we can basically interpret these plots. So this is the field or the output solution field for a particular sample as it grows in time. And these are the 4 different rows which are there underneath. They basically represent the absolute errors between the ground truth and the predicted solution profiles. That's why you see a different color map. In the training domain, we only show one of the time step because it's very short. And as you can see, autoregressive has higher errors, and this accumulates errors early on, and then it quickly deviates from the actual profile at the first few time steps itself. It still persists with that bad performance. Full rollout you can clearly see that it does good in the training temporal domain. The performance sort of translates to some of the time steps beyond the training domain, but for a longer time horizon, you can see that the TI-DeepONet frameworks sort of edge ahead, and because they're able to mitigate the error accumulation which happens when you're simulating for a long time horizon. And again, within the two TI-based frameworks, TIL does slightly better, although I'm not sure if the difference is observed here, but we can see the relative error plus where you can clearly see the difference. And again, the TI-DeepONet does the best job out of all. Moving on to the relative error plots, here you can see autoregressive blows up, there's a rapid error accumulation, and there is a monotonically increasing trend. Full rollout, we would say that initially it does perform better, but since it learns a fixed basis, like it learns a set of fixed basis functions and coefficients, which are basically tailored to the training temporal domain, right? This limits temporal generalizations, and these basis functions are not sufficient or enough to represent the solution states in the extrapolation domain. And this is what you can see, like beyond a certain time point, the TI-DeepONet edges ahead and does perform better than the full rollout. And within the three different TI-based frameworks here, TI-DeepONet, AB, and RK4 were almost quite similar, AB having slightly better accuracy, but again, uh, the TIL-DeepONet, as expected, as is consistent with the other examples that we saw previously, TI-DeepONet gives you the best performance with having a very decent final L2 error of about 15%. So this is more or like a 3x extrapolation that we did, because we gave 1/3 of the training time domain of 1/3 of the temporal domain for training, and then we did the extrapolation on the rest of the domain. So this was quite decent. And the final PD which we'll look at is the two-dimensional Allen-Kahn equation. So this equation has applications in modeling phase separation and interface dynamics, and this is also a nonlinear parabolic PD with bistable states. So why do I say bistable states is because you can be either in plus or -1 depending on which phase you are, and the PD has sort of this form. So this epsilon is the interfacial width of the diffusion length, and higher the value of epsilon, more is the numerical dissipation characteristics of this PD. Apart from that, we also have a reaction term, which is minus of u cube minus u. So the Allen-Kahn equation can be thought of as an example of a reaction diffusion system. So a reaction diffusion system has two components. One is the diffusion component, and one is the reaction component. So there is always an interplay or a competitive behavior or a competition between these two terms, and that essentially governs the actual PD dynamics that we see. Again, in this case, we consider a very similar spatial temporal domain as the Burgers equation. Here, the time domain is again from t equal to 0 to 1, and we take in a similar spirit, we take the first half of the temporal domain for training, and then we do the extrapolation on the remaining temporal domain. Moving on to the results. So here, what we observed was DeepONet autoregressive has errors which are orders of magnitude higher than the three different frameworks. And I'm not sure if the color bar is visible, but the magnitude of the errors in the autoregressive case are much, much higher as the other three different frameworks. Now, these three rows that you can see are basically plotted in comparison to the full rollout color bar, which is like shown here. And as you can see, full rollout, so the TI-based frameworks do better than the full rollout um, in the training domain, and that's also translated well to the extrapolation domain. So again, here what we observed was the performance difference between the TIL-DeepONet and TI-DeepONet was not that high. And essentially, we could use either of these frameworks for this specific PD. Uh, Moving on to the final set of results. So again, we see a huge error accumulation in the DeepONet autoregressive case. Full rollout has a very non-monotonic or a non-definitive pattern, and in the L2 errors, and for most part, it is not performing better than the TI-DeepONet. But for a specific region, let's say I think it's around 0.35 to 0.65, full rollout does slightly better than the TI-DeepONet. Again, this behavior has no specific explanation because in the full rollout case, as I mentioned, we are not enforcing the causal structure in the system. Instead, we are trying to represent through basis functions and coefficients, right? But beyond a certain time point, so this was also observed in the Burgers case, right? For a longer time horizon, as you move further and further in time, we can expect this error in the full rollout to keep on growing as you move further in time. But TI-DeepONet sort of would have a more controlled and stable error growth as you move further in time. And one of the key highlights or one of the key observations that you can observe in all the different PD examples is that the error growth in the TI-DeepONet framework is controlled, as well as for a longer time horizon, we can see this plateauing behavior after a certain time point. So we expect that as you simulate further and further in time, these errors are going to reach a sort of plateau and will not increase further. That is what we expect. Uh, Again, within the TI-based frameworks, as I mentioned, TI-DeepONet does very slightly, does slightly better, but the improvement was sort of minimal over the other frameworks, as you can see. Finally, this is my summary slide of all the results that we saw. So the way you can interpret this table is as follows. We have the 5 different PD examples that we considered, and basically the T here refers to the start time of the extrapolation domain, and T star is the final time step. So these values that you can see are basically the relative L2 error values that were observed like quantitatively in the extrapolation domain only. So note that these 4 values or these 4 columns only show the relative L2 errors in extrapolation. And you can clearly see that the highlighted bold-faced values are represented by the TI-DeepONet framework. And you can consistently see that all the 5 PD systems, barring this exception, TI-DeepONet emerges out to be sort of the best method of all, and it has the lowest relative L2 errors observed across all the 5 examples. Finally, I would want to conclude with this slide. So in this work, we introduced TI-DeepONet and its adaptive variant, which is the Learnable TI-DeepONet, which basically integrates classical, well-established numerical time integration with operator learning frameworks. We saw that TI-DeepONet sort of reduces roughly L2 extrapolation errors by 81% compared to autoregressive setting and 70% compared to full rollout methods. And it also maintains stable predictions for temporal domains, which are extrapolation domains, which are basically twice or thrice the training interval. And the learnable coefficients that we employ in the TI-DeepONet further refine accuracy by adaptively weighing the intermediate integration slopes. And one thing to note is that the difference in the TIL and the TI was observed to be quite significant in the 1D Kuramoto-Shibashinsky equation. So recall the 1D case PD was a chaotic PD, right? And for a longer time period, we could observe the use case or the benefits of using an adaptive variant. As you can see, there's a quite a significant difference between the relative L2 errors that was observed between the fixed variant and the adaptive variant of the TI-based framework. Now, all of this were all the good things, but it is also my responsibility to mention one of the main limitations of this framework, which sort of also forms a future work, which is that, as you can see, the if we keep on using higher order numerical integration schemes, that would basically mean multiple forward and backward passes through the ODE solver, right? So that essentially leads to a higher compute cost during training and also during inference as well. So that's one of the major limitations, as we say, of this method. And moving on to higher or more efficient version of this method forms one of the key future directions of this work. So I think I would stop here, and I'd be happy to take any questions.
Thank you very much, Dibyajyoti, for a very nice presentation. So now I think I'll ask the audience if they have any question. I think Rajat had a question, and so Kunal also seemed to have a question. Maybe we'll start with Rajat's question, and maybe I'll rephrase. I also had a very similar question, and Rajat can actually also correct me if he has the same question. So that was, I think, on slide 6. If you could go back to slide 6, maybe. Yeah, maybe this slide is also fine. Yes. So I think Rajat's question and my question were similar in the sense that what are you doing in this OD solve? And if I understand, let me just try to say that what I understand, maybe you can correct me. So in this OD solve, you have the actual PD, but you have actually substituted the values of UX, U meaning that here it's the user solution. So solution you have at the time as well as the time derivative, the spatial derivatives U and UX, U double X, whatever it is there in the actual PD, you have actually substituted the values of U, UX and U double X and all of these. It is only the time that is remaining, and that is exactly what is making it into just an ODE after you have substituted for these U, UX from your DeepONet, right? And then you're just solving the ODE using a solver like RK4 or something else, right?
Is
that
so,
what you're doing in the ODE solve?
Yeah, exactly. So, I mean, that's precisely what I'm doing. So, the main idea is that if you consider a general PD, a general PD can be represented by like partial U over partial T equal to some right-hand side, right? And that right-hand side is basically, parameterized by U and its, corresponding spatial derivatives. You also have time, but in this work, I would like to mention that we only consider autonomous systems. So the right-hand side is independent of time. So it only is a function of the solution at that particular time and its corresponding spatial derivative. So the main idea is to basically parameterize the right-hand side completely through the neural operator. And that's why you have the spatial coordinates sitting here in the trunk network.
I think that was probably what Rajat was trying to ask. Okay, so we have a few other questions. Maybe I read them out. So Mohammad Rifat Hussain has AI's well-vet. Salam, hope you're doing well. Basic question. Functional mapping.
No, Kunal is the question, Rajdeep. The other questions are from previous.
Oh, I see.
Kunal
I see.
is
Yeah.
the first.
Okay. Yeah, right. Kunal has a question that how does TI-DeepONet perform under data scarcity or when trained on irregularly sampled or non-uniform time steps?
Yes, so that's a very good question. We haven't explored that. So in this case, we only considered a fixed delta T for our use case, but you could extend this framework to account for non-uniform delta T. So if I understand the question correctly, you might sample the solution states at some random locations in the temporal domain. So is that what the main question is?
I believe, yeah. So,
yeah. So
second question, yes, please go ahead.
Yeah, so you could do that because the main idea behind this framework is that given any solution at time t and time t plus 1, you are basically approximating the RK4 or the numerical tangent, which is basically connecting those two solution states. And right now, I do not have an answer as to irregularly sampled solution states because in this current framework, maybe one of the limitation is that you always need a pair of UT and UT plus 1 in order to approximate that time derivative between the two solution states. So Yeah, but that is something we can, work on as well. It will require some modifications to the architecture, but that is possible.
I think if you just change H to a adaptive H, I mean, meaning that depends upon the irregular sampling, the H is the one
Yeah,
that is needs to change. I think that
yeah,
this
yeah,
can be
yeah, yeah,
accommodated.
yeah. We can,
Yes. Right.
yeah. We can use the
So the
H
second
here.
question is from Abdul Hanan Mustajab. So he is asking, have you ever tried this method to solve equations which have second order time derivative or equations which are like wave type equations? What would you
Yeah,
think
so
would be the performance of this framework? So I think that the examples that you've taken are not like wave type equations or do not have
yeah,
second order time derivatives.
second order
So
in
how?
time. Yeah. So that's a very good question. And one solution that I can quickly think of is that I can try to convert that system into two first order in time two first order in time PDs. So you can use, like if you have a wave equation, you have displacement and you have velocity. You can use the TI framework in a basically a coupled manner. So in that case, you'll have two ODE solvers, which will independently numerically integrate the velocity and the displacement. So you can solve it in that way um, by
Yeah.
converting into a first order system.
Yeah. So yeah, so I think your framework is not restrictive to just these equations. It can also handle wave type equations, right? Yeah. So
Yeah.
any other questions? I have one question. If I will just ask others if they have any other question.
Rajdeep, go ahead. I have one question, but I will ask at the end.
Okay. So yeah, so this is probably a question and a suggestion maybe. So Dibyajyoti, I was thinking like, so in this particular slide, you have the MSE loss, which you're comparing with just the next step, right? So you're taking UI and you're comparing that with UI plus one, right?
Yeah.
So
Yeah.
would it not be good if you also had included UI plus one, UI plus two, UI plus three, and maybe UI plus maybe some M, or of course, here you're using M for a different reason. So I could, let's say, I plus S, where S is a short horizon window which you are taking, which means that you are
Yeah.
basically taking a input and you're also trying to propagate through the OD solve to the next few time steps, and just trying to kind of have a little bit more stability, because that way it will just take it as an initial condition and then solve it. Maybe
Yeah.
did you think about it?
Yeah, so I mean that was something which we had in mind. So what you're basically suggesting is inform the network of maybe not the immediate future step, but uh, 5 steps ahead, let's say,
Yes.
like a sort of temporal unrolling forward.
Yes,
So
through the
and
OD solve.
then
Through the
yeah,
OD solve.
through the
Yeah.
ODs, yeah, and then take a basically a summation over all those losses.
Yeah.
Uh,
A weighted summation
so.
maybe.
Yeah. So that's a very good suggestion, and I think this is called temporal unrolling. This has been, so this is I think this has been shown in the literature that it sort of enhances the accuracy. But yeah, this is something which we can do that is very much possible. And as a follow-up thought, uh, you could also include solutions at the previous time steps here, alternatively. So in order to update the solution at time t plus one, I'm only using u at time t. But you could also take a window, like some sort of a memory in which you could also give u at time t minus one, t minus two, or t minus three. And then basically the u at time t plus one would be a function of all the maybe like uh, previous 3 time steps as such. But here we did from t to t plus one because I mean we assumed it's a first order Markov chain. So,
Hmm.
but uh, like that is a very simplified assumption that I completely understand. We could enhance it further.
I see. So I have two more questions, very short ones. One is
Yeah.
that here you're trying to forward solve for an OD. So you have UI and you're getting UI plus one and then doing an MSE. Is it also
Right.
possible that you have UI, you backward solve UI minus one and also forward solve UI plus one and then have a mean squared error, because you can always use the OD solve to actually backward solve or forward solve, right?
Right. So
So,
what you're suggesting is basically a modified Euler method or
yeah, just
something
you can.
like a weighted sum of forward and backward
Right.
slopes, right?
Possibly you
Yeah.
could explore that. Yeah.
Yeah,
So
yeah. I think that's a very good suggestion. I think, yeah, that is very much possible. Yes.
So the last question
Um,
that I have is regarding that you had mentioned that you could actually during training take the OD solve as let's say RK4, and while testing you could use a different scheme for OD solve, right? So
yeah.
yes, I mean in theory you can use, but does it not typically increase the error if you are using a lower order scheme for during prediction and a higher order scheme during training?
True. So
It will
that's, I
increase
think,
the probably the error would increase by a little bit at least, I would expect,
yeah,
because
yeah.
the entire network parameters were trained using a certain ODE solve, and then suddenly when you see it give you a different solver, then the errors might actually, because the same parameters are no longer valid for, I believe that's probably my
Right.
assertion. Is that correct?
Right. Yeah. That is very much correct. That's why, I mean, this is more of an implicit thing that we did. So we did use AB to AM3, the Adam Bash for the Adam Martin predictor corrector, and AB to AM3 has, I think, if I'm not wrong, order 4 accuracy. So it's similar to RK4. So that's why I feel that we could use the same scheme, but yeah, you are exactly on point, Professor, that we cannot go with a completely different scheme. We also have to account for the order of accuracy. And yeah,
Thank you so
probably
much.
a lower order scheme would result in more errors. Yeah, that's correct.
Yeah. Thank you so much, Divya, for the answers. Very good work. Yes, Savik, please go ahead.
Thank you.
Yeah. So hi, Dibya.
Hello, Professor.
So to follow up on Rajdeep's question, so if you take, I mean, again, I'm trying to think out loud, right? That if you take, let's say, ui plus one, ui plus two, I plus three, and form the loss function, will
Right.
that also have some? That might also have some vanishing gradient problem, right? When you do back propagation through that,
Yeah,
or will
so
that
I feel
will that not have?
no, I think you're right because there is something known as back propagation through time (BPTT)
Yeah.
behavior, which
Yeah.
is so this is a common problem in RNNs. I think
Mm,
uh, yes, that is very much possible, and in that case, we cannot. I think we cannot maybe take a simple summation of the future solution states, but maybe uh, like weigh the contributions by some factors because. All the future solution states might not be that important, and we can maybe use adaptive factors, and we can
yeah.
make them learnable as well. So I think I'm not sure if that will solve the problem.
I mean, yeah, yeah, maybe not, but that's okay. I mean, that was actually not my question because Rajdeep asked. I thought
uh,
of yeah, that came to my
yeah,
mind.
yeah,
So
yeah,
so I have basically two very short questions. So when we
right,
do some time integration scheme, right?
right,
Uh, we know that it has an order, which means it has an error. The error is quantifiable, right? Second order, third order, fourth order. We know that.
right.
Uh, so to again, this is kind of a follow up before I ask my actual question. Is that did you try training on using a low order and then predicting using a higher order method?
Uh, the short answer is no, because we so the main theme was basically to uh, mitigate the error accumulation and give the neural operator some sort of extrapolation capabilities. But there could be a rigorous numerical analysis as to uh, what kind of numerical method you should use in training and inference. But I, so the long answer is I think it would not give good results because let's say we use an Euler, first order Euler explicit, and we use RK4 during inference. Uh, since the network has learned the tangent or the temporal tangent between in sort of a first order. I mean, it's not an accurate, I mean, tangent. So a higher order scheme during inference might not be sufficient in order to course correct the tangent, which was learned with the first order scheme. But yeah, that is something we didn't try, but it is, yeah, worth
Yeah, I
exploring, I would say.
ask it because what I'm really interested in to see actually, and this is my actual thought, is that whether the learnable TI-DeepONet is actually giving you result which is maybe a order higher or maybe approaching order higher. Because if that was
Okay,
possible, then you
okay.
could compare and then you can understand that, okay, because you are learning, maybe the order, that error is getting reduced, the time integration.
Right,
I do not
right,
know, but I
right.
think that if that was possible, you could compare.
Right.
And
I think
yeah,
this has been a concurrent suggestion that it would be a good exercise to basically do a theoretical error analysis as to what order of accuracy are we getting under different combinations of numerical schemes.
yeah,
And then we could really maybe, I mean, theoretically
yeah.
show the benefits of the learnable variant.
Right, right. Because you have two types of error, right? One is the learning error or learning uncertainty, whatever you call it, because you are learning approximately. The error is not zero. And the second one is the
Right.
numerical, because you are using a ODE solve. So
OD
you
solve.
are,
Yeah.
so I agree with what you said. The second question is like one line question is that because it is about time integration, right? Did you
Right.
try some steep differential equation? Because there the
Not
time
yet.
step is very small and all those things,
Yeah.
all those issues comes into
Yeah.
picture, right?
So that is one of the, I mean, things that I'm working on is basically, uh, can we, couple shock capturing schemes here like ENO or VNO schemes, and
Mm.
then that will help us maybe, capture shock-like behavior or, as you said, stiff dynamic systems.
Mm.
So that is an ongoing work that we are doing. Yeah.
Okay, okay. Uh, yeah, so that's all from my side. So is there any other
Right.
questions? If not, let me thank you again for
Thank you.
Thanks,
presenting on
Dibyajyoti.
such a short notice. And we'll close it and we'll meet again next week. Thank you.
Thank you so much.
Goodbye. Goodbye, everyone.
Bye. Bye all.